Hello and welcome back to the channel. Thank you for taking some time out of your busy study schedule to come and do some maths with me on Mathematics. Today we are trying a different kind of video that I've never done before. I couldn't decide on one topic to do a revision video on, so I'm going to do a little bit of everything. In this video, I'm going to take a look at 5 questions from the 2023 Extension 1 HSC exam. 5 questions that I think are interesting or that I might be able to provide some insight on to help you with your study, in the hope that you'll see one of these in the 2024 or beyond exam and then smash it. So I'm going to start off with multiple choice, and then we're going to do one from each of the 4 sections. And most of these are pretty tricky, and we are going to cover a band 6 question today. So it is going to get spicy, so strap in. Okay, starting off with an interesting multiple choice question from 2023. We have a cubic function shown below. We have the graph, we don't have the equation. Which of the following functions shown on the right has an inverse relation whose graph has more than 3 points with an x-coordinate of 1? So straight away seems like a lot of work, because it seems like we've got to sketch these 4 graphs and then sketch all their inverse relations to then see how many of them pass through x equals 1 3 times. But actually there is a trick here, okay? If we want to analyze the inverse relation of these 4 graphs and we want to see where they have an x-coordinate of 1, where the inverse is going to have an x-coordinate of 1 is where the original function is going to have a y-coordinate of 1, okay? Because remember, going from an original graph to its inverse is just swapping the x and the y's. So the shortcut here is that if we're trying to find which of these 4 graphs has 3 points with an x-coordinate of 1, we're just going to look at them and see which of them have a y value of 1 happening more than 3 times. Okay, so we're going to very quickly sketch these 4 graphs and see which of the 4 crosses this red y equals 1 line more than 3 times. Okay, so you do need to know how to sketch all 4 of these to access the question, although thankfully the answer is just the easiest one. But anyway, sketching on screen is pretty tough, so I'm going to step over to my good friend Desmos to help me out with a bit of very clever editing that I'm not going to do. Okay, here we have Desmos. We have the original graph that I've tried to recreate to the best of my ability, and now we're going to look at the square root, the reciprocal, the absolute value of the input, and the absolute value of the output. So first of all, the square root graph looks like this. Everything below the x-axis is negative, so we can't take the square root of that. The square roots are the same thing at 0 and 1, so we're crossing over at 0 and 1. And of course, if you're above 1, then the square root is smaller than the original function. If you're between 0 and 1, the square root is greater than. But you don't really need to know that. All you need to see is where they're crossing over, which is at y equals 1. And we can see the green graph is hitting that y equals 1 line on 3 separate occasions. And we're trying to find a graph that does this on more than 3 occasions. So that's no good. Let's now have a look at the reciprocal. So the reciprocal graph, of course, is going to have asymptotes wherever the original graph is equal to 0, because we can't do 1 divided by 0. So we have an asymptote here, here, and here. Important to note that the reciprocal function and the original function cross over when the function is equal to 1, because 1 is its own reciprocal, and so is -1 down here. So once we've got a bit of a sketch of that done, we can see them crossing over 3 occasions, and the green graph, which is the reciprocal, is crossing over the y equals 1 line on 3 occasions as well. So the green graph is not going to have more than 3 y coordinates equal to 1, which means its inverse is not going to have more than 3 x coordinates equal to 1. Okay, next contender is the absolute value of the input. So what happens here is all of your negative x values on the left-hand side, when they get put in the function, they get absolute valued, so they turn into the same answer as the right-hand side. Okay, so the absolute value of the input just takes the right-hand side of the graph, right-hand side of the y-axis, and reflects it across the left. So we get this shape here, as we can see from before. Okay, what's important here is this green graph is now crossing the line y equals 1 on 3 occasions, just like the last 2. So it's no good. We need it to happen more than 3 times. So it must be the last one, which is the absolute value of the output, which is going to take all of our negative y values and reflect them above. Okay, so the little negative part down here flips up, and the negative trend down here becomes a positive trend. And now what do you know? This absolute value graph is passing the line y equals 1 in 1, 2, 3, 4 occasions, which means its inverse relation will pass through x equals 1 on 4 occasions. So that's going to be our answer. So going back to the question now, the one that we're going to pick is D, which is y equals absolute value of f of x. I guess the good news here is that if you knew this shortcut, the easiest one that's graphing, so if you went backwards and started with D, you would get it straight away, whereas these three are a little bit tougher to graph. But other than that, that's the shortcut to approach this seemingly complicated question in an uncomplicated way. Okay, moving into the short response section now. Starting off with the question from the first question set, which is 11. The one I've picked is to solve cos theta plus sine theta equal to 1 for theta between 0 and 360 degrees. Okay, so there's not much guidance given here. They haven't told you what method to use. So to answer this question or to access it, you need to know that equations in this form, where you have a cos and a sine equal to a number, they can be solved in one of two ways. You can either use the auxiliary angle technique, which is the r cos theta, r sine theta, that I've done a fair few times on this channel. Something I haven't done a few times on this channel thus far and can be used here is a t-value substitution. Okay, so when you have a cos and a sine and you want to simplify the equation and make it easy to solve, a t-sub is going to be a good option here. Okay, so in case you haven't memorized your t-value substitutions, you go to your reference sheet and they're right here for you. So letting t equal to tan theta on 2, cos theta is going to become 1 minus t squared over 1 plus t squared, and sine theta is becoming 2t over 1 plus t squared. Now we're just going to solve this equation for t and then back substitute that t is equal to tan theta on 2 and then approach it like that, with a few things to remember as we go along. So the easy part is the algebra. The first thing we're going to do is get rid of all the fractions by multiplying everything in the equation by 1 plus t squared. So now there's no fraction here, there's no fraction here, and the right hand side becomes 1 plus t squared. Okay, now because it's a quadratic, we're going to group everything together. Let's go over to the right hand side. So we'll add this across to make 2t squared and minus this across to make minus 2t. Now we can just factorize, taking out the common factor of 2t. So we have 2t outside of t minus 1 equal to 0, giving us our two solutions for t as 0 and 1. Okay, so we know what t is. Now we've got to figure out what theta is. And remember, t is equal to tan of half theta. Okay, so the first one is when t is equal to 0. So we're trying to see what tan theta on 2 equal to 0 solves to. Keep in mind here that because theta is between 0 and 2 pi, or 0 and 360, theta over 2 is going to be half of that. So it's going to be between 0 and pi, or 0 and 180. So to solve these two equations, we're only going to be looking at the first two quadrants. Okay, theta on 2 between 0 and pi. Okay, so where is your tan graph equal to 0? Tan is equal to 0 at every multiple of pi. So the first two that are going to work are 0 times pi and 1 times pi. Again, we don't need 2 times pi because it's outside of the range of theta on 2. Okay, so now we'll just double these and we'll get theta equal to 0 and 2 pi. Now for the other one, that's when tan theta on 2 is equal to t when t is equal to 1. Okay, so in the first two quadrants, the only time when tan gives us an answer of positive 1 is when the angle is equal to 45 degrees. Okay, the next solution is going to be in quadrant 3, which is outside of our range. So theta on 2 is equal to 45 degrees, or pi on 4. And so we multiply that by 2 and we get theta equal to pi on 2. Okay, so there are our three solutions. Before we conclude, there is something you are meant to remember to do for a t-values question that sometimes can be important, and it's to do with 180. Okay, if you've looked at a tan graph recently, you know that tan is undefined when the angle is equal to 90 degrees, or pi on 2, which means that when you're doing a t-sub formula like this, if pi is one of your answers, the t-sub is not going to find it, okay? Because tan is undefined at 90, when theta is equal to 180, it's not going to tell you whether it's working or not. So we're supposed to check every time we do this, okay? Doesn't take very long. We just go back to our equation and we just chuck in theta equal to pi and we see what we get. So cos pi plus sine pi. Cos pi is -1 and sine pi is 0. So adding these together, we get -1. We don't get 1, which is the answer. So this is just us double checking that theta doesn't work, that pi doesn't work as a solution. Now we're ready to conclude and get our 3 marks and say that theta is 0, pi on 2, and 2 pi as our final answer. Okay, so the whole trick here was just looking at the question and just knowing your stuff and being like, okay, cool, there's 1 or 2 options here. T-values is probably the easiest one. Okay, moving on now to a question from the next set, from question 12. Okay, scary looking question, but really not that scary. It's a band 4 level. So we have NCR is equal to n minus 1 CR minus 1 plus n minus 1 CR. This is really just a fancy way of saying that in Pascal's triangle, if you want to get one of your coefficients, one of your combinations, it's just the sum of the two combinations above it. Okay, so when you're filling out your triangle, hopefully you did this in your combinatorics topic, you add two numbers together to get the number below. That's all that's saying there. Okay, so find one possible set of values for P and Q such that bloody blah is equal to P, C, Q. Okay, so we're going to try and combine these three combinations together into one combination using the formula prescribed in the question. As with all my revision videos, best way to get value from these is to, once I've explained the question, is pause it and have a crack yourself and see if you arrive at a solution that's similar to mine. Or maybe we'll approach it in different ways and your learning will be completely enriched. It's hard to say. All right, so first thing we can do is look at these two combinations here, the 2022s with the 80 and the 81. Now, comparing this to the formula given to us in the question, the way I'm reading this formula is when you have two combinations and the top numbers match and the bottom numbers are one apart, we can combine these two combinations together by increasing the top by 1 and taking the larger of the two bottom numbers. All right, and now these two combinations fit this bill because we have the top numbers matching of 2022 and our bottom numbers are 80 and 81. So using this and combining these together, we're going to increase the top number by 1 to 2023, and we're going to take the largest of the bottom two numbers, which is 81. Okay, that's how we combine these two combinations using the formula given in the question. Okay, now, so that's the first two numbers done. The problem is that the next combination is 2023 at the top, which matches, which is good, but the bottom number is 1943, which is nowhere near 81. So we've hit a bit of a roadblock here, okay? And the solution here is to recognize the relationship between 1943, 81, and 2023. Maybe you might already know this if you have a grandparent who was born in 1943 and they're 81 years old, and you would know what their age is last year. Anyway, I'm rambling. What I'm saying is that combinations are symmetric. For example, if you have something like 6C2, it's going to be the same thing as 6C4. That's why all the rows of Pascal's triangle are always symmetric, okay? If you're counting up or counting back, you're going to get the same combination. What that means is because 2023 take away 81 is equal to 1942, that tells me that 2023 C81 is the same thing as 2023 C1942 because this one is 81 steps up and this one is 81 steps back. Okay, so recognizing this this symmetry is really important answering this question. We can say, all right, 2023 C81 is the same thing as 2023 C1942. Okay, now we're ready to incorporate all this red knowledge into our left-hand side of the equation and try and combine them together to make one combination. So for the left-hand side, we've combined the first two combinations using the first red line. Okay, so these two have turned into 2023 C81. Now we're going to use this second fact and we're going to change the 2023 C81 to be a 2023 C1942. Okay, now we have two combinations where the top numbers are the same and the bottom numbers differ by 1. So using the original formula again, we can say, all right, we're going to combine these together by increasing the top number by 1 and taking the larger of the two bottom numbers. So our top number is going to increase to 2024 and we'll take the 1943 as the larger of the two bottom numbers. So we end up with 2024 C1943. So that's one of the solutions to this problem. I know there's at least two answers that fit the bill to get 2 marks. So if you got another set of numbers or a different value of Q that you think is correct, let me know in the comments and I'll let you know if you're spot on and you'll get respect of your peers and likes from people in the comments. Okay, that's question 12 done. Let's move on to what is probably the hardest question from today, which is from question set 13. It's got 3 parts and they range from an easy band 3 up to a really spicy band 6. We have a hemispherical water tank, you can see here, radius capital R, and it's got a hole at the bottom to let water drain out. Initially, there's no water in the tank, and then it's being poured in at a rate of 2 kR. That's going to be important later on. K is a positive number. After t seconds, the height of water is given by h and the volume is given by v. So far, very straightforward. We have water pouring in, but we also have a little bit of water pouring out through the hole. So it's a lot of derivatives and variables going on here. Okay, looking at the first part of the question, we have, it is known that the volume of the hemisphere is given by this, and they've asked you to do not prove this. Okay, this is really important. If you prove this in the exam, Nessa will come to your house and punch you in the head. So do not prove it. Don't waste your time. Okay, while water flows into the tank, it also drains out the bottom at a rate of change of the volume is given by this. Okay, so this is our complete rate of change of volume formula. We have water flowing in at 2 kR, which the question mentioned, and we have water flowing out the bottom at minus HK. Okay, so water in and water out combined gives us this. Okay, first 2 marks, show that dH on dt is equal to K over pi h. All right, so there's a lot of variables here, and we're trying to chain together a dH on dt. So we've been given an equation for volume in terms of the height. So probably a good place to start would be to differentiate that to get dV on dH. Okay, the more derivatives we have, the more we have to work with, and we can chain together and make a dH on dt. Okay, if we differentiate this with respect to h, this 2 is going to come down. Pi is just going to chill out the front. Okay, constants are just left to the side when you're doing calculus. The 2 comes down the front to make 2RH, and the 3 comes down the front to make 3h squared over 3. And again, pi just chilling out the front. This can simplify because 3 over 3, which I believe is equal to 1. And then you can even be a little bit more fancy here and factorize this by taking out the common factor of h to make it look like this. This is good because we've got a 2r minus h here and a 2r minus h here. So things are matching up. Okay, now we don't have an equation relating h and t, but we can build this derivative by doing what's called the chain rule or the related chain rule, and splitting this apart into a dH and a dt, and then filling the gaps with the extra variable that we have to work with, which in this question is quite clearly volume. So we're going to put a dV here and a dV up here. Okay, so when you don't have an equation relating these 2 variables, look at the equations that you do have and figure out how you can chain together to make this. If this part's really scaring you, I have a whole video called Related Rates of Change that can show you how to do more of those. Okay, so over here we have dV on dH, which is just here. So dH on dV is just going to be this, but upside down, so it's going to be the reciprocal. dV on dt has been given to us generously by the question. So chucking all that in, we have the reciprocal of our derivative over here, and we have the dV on dt provided. And again, conveniently, we have a 2r minus h on top and bottom, which is just going to cancel out, and it's going to leave us with a k on top and a pi h on the bottom, which is the target for 2 marks. So far, 2 out of 2, nothing stressful so far. That's probably the band 3 part. The next 2 parts are the 5 and 6R. Speaking of, moving on to part 2, which is show that the tank is full of water when t is equal to pi r squared over 2k seconds. Okay, and given that we just built an equation in part 1, relating h and t, we can probably use a bit of calculus here to figure out an actual equation relating h and t, and then figure out how we can build this expression to satisfy the tank being filled. Okay, so we have a differential equation here. Because the top variable is dH and the right hand side is in terms of h, there's no t's. That straight away tells you should start by taking the reciprocal of both sides. Okay, when the variable on the right hand side is the top, you want to start by flipping, because now we want to multiply this dH across the right and integrate. Okay, so if we integrate the left-hand side, we're going to get t, and we're going to integrate the right-hand side with respect to h. Okay, so we have pi h over k. Pi and k are just constants, so we're integrating the h by making this an h squared over 2. And of course, don't forget your constant because you just did an indefinite integral. So t is equal to pi h squared over 2k plus c. Let's very quickly figure out what the constant is by using the fact that initially, so when we started this thing, there was no water in the tank, which means that height was equal to 0. So when t is 0, h is 0, you chuck those both in and you very quickly figure out that the constant needs to be 0, which is very convenient. This gives us our equation of just t equals pi h squared over 2k, and now we're trying to find the time when the tank is full of water. So think about what happens to this height of water when the hemisphere is full. Suddenly the height becomes the distance from the center to the edge, which is known as the radius. Okay, so when the tank is full, the height is going to be equal to the radius of the hemisphere. So tank is full, h equals r, chuck that in and we get t equals pi times r squared instead of h squared divided by 2k, which, hey, what do you know? That was the target for another 2 marks. So 4 out of 4 done, piece of cake so far. Now we move on to the mind-numbing band 6, part 3 for 3 marks. Okay, part 3, the instant the tank is full, water stops flowing into the tank. That's important because it's going to change our derivative. but it continues to drain out of the hole at the bottom as before. Show that the tank takes 3 times as long to empty as it did to fill. So I've just put over on the left here all the derivatives we've been working with so far, and we're going to see how we can use these to try and answer this question to get 3 marks for a band 6. So show that the tank takes 3 times as long to empty as it did to fill. Well, in part 2, we found that this is the time taken to fill. So we're trying to find the time to empty as 3 times that. Okay, this is our goal for this question. Show that the time to empty is equal to this. Okay, like I said, the important part about this question that's tough to realize is that once the tank is full, water stops flowing into the tank. That means it's going to change our derivatives, it's going to change our rates of change, which is going to change the equations we've worked with so far. So we've got to make some changes and then kind of redo a bit of stuff. So we're going to start with our rate of change of volume. Okay, this is the water flowing into the tank from part 1 and 2, but this includes the 2kr, which is the part going in. Okay, once we've filled it, we're not going to keep putting water in, it's just water coming out. So expanding this out, it makes it a bit clearer to see that this derivative has a positive part and a negative part. The positive part was the water flowing in the first 2 parts of the question. The KH that's negative, that's the water that's flowing out the bottom of the hemisphere. Okay, so our outflow equation that we're going to now use for part 3 is dV on dt equal to minus KH. That means we need to go back and make a new equation relating time and height using a similar trick from before. So before we did dH on dt by chaining it apart with a dH and a dt here and filling the gaps with dV. Okay, the relationship between height and volume has not changed, so we can still use the dH on dV from before, but now our dV on dt, because we are just outflowing as opposed to inflowing as well, now our dV on dt needs to just be negative KH. Okay, so same dH on dV as before, this is from part 1, and dV on dt is minus KH. Okay, so combining that together, we get this expression here by putting the minus KH on top. And now because there's an H on top and bottom, we can cancel those out and we get dt on dH. Oh, sorry, I should have mentioned that going from here to here, going from dH on dt to dt on dH, I just flipped them. Okay, so this line and this line are just reciprocals. H's cancel out, and here is our best expression for dH on dt. Okay, now, just like last time, we're going to use this equation to create an equation between time and height. Because last time we were seeing when the tank was full, which is when H was equal to R. Now we're trying to see when the tank is empty, which is when H is equal to 0. Okay, so there's our approach. This is now our differential equation that we are going to attempt to solve. So let's do that. Let's put it up here. So we've just integrated the left-hand side to become t, which means we've got to integrate the right-hand side. So integrating this fraction with respect to h. Making that a little bit simpler by putting the minus pi over k out the front to just not worry about it for now. And now integrating 2r minus h with respect to h. So the constant 2r is going to get a variable, so this will become 2rh. The h integrated is going to become h squared on 2 because of the power rule. While we're here, it's going to make it a little bit easier and nicer for our working out to just multiply the negative k across the left and then divide by pi. So just putting these constants across the left with t, it's not essential, it's just going to make my working out a little bit clearer for you guys. So 2r becomes 2rh, h is becoming h squared on 2, and we have a constant once again. Okay, so our initial condition is to figure out our constant. Now because this is the model for our outflow, the initial conditions have changed because now we're starting from when the tank is full. So our initial conditions are that when time is 0, the tank is full and the height is equal to the full radius. Okay, that's really important here. So left-hand side just becomes 0, thankfully. We have 2r times r, which is r squared. We have minus r squared over 2, and we have a constant. Okay, now to figure out our constant, we have 2r squareds, take away a half r squared, which is 1.5 r squareds, or 3r squared on 2. Moving that across the left gets us that our constant is negative 3r squared on 2. Now we're just going to put that back into our equation up here where we saw a c. We're going to replace it with, that's funny. We're going to replace it with a minus 3r squared on 2. Now here is our equation. Okay, we don't really need to tidy this up. We just need to use it. And remember, the goal here is to find the time when the tank is empty. And when the tank is empty, what's the height? The height is equal to 0. So that's how we're going to finish this off and get our third mark. So find the time when h is equal to 0, which makes the tank empty. So we have minus kt on pi on the left, we have a 0 here, we have a 0 here, and we have a minus 3r squared on 2 here. The zeros don't do anything. We can take the negative off both sides to get kt pi equals 3r squared on 2. Now we can just times the pi across and divide the k, and we're going to get 3 pi r squared over 2k, which, would you believe, is the same answer from before, which is pi r squared over 2k, but it's been multiplied by 3, so therefore the time to empty is 3 times the time taken to fill, and there's our 3 marks acquired for this band 6 question. Oh boy, that was fun. I hope you had fun. I had so much fun. All right, let's finish off with a question from question 14, which isn't as scary as this one. It just has a little trick that needs to be seen. Otherwise, it's very hard to access the question. So here's one from question 14. It's a band 5 level. We have a function equal to 2x plus log x, and x is positive. Starting off with part 1, explain why the inverse of f of x is a function. Okay, so for an inverse to have a function, it means the original function needs to be a one-to-one function. What I mean by that is, here's an example of a function that would have an inverse function because it's always increasing and it's never looping back on itself. Anywhere we cut this with a horizontal line, it means that the inverse is only going to be cut by a vertical line once. So it's called a one-to-one function, or a monotonically increasing or decreasing function. So this is an example of a function that would have an inverse function. Here's an example of something that would have an inverse relation, but it wouldn't have an inverse function, okay? Because you can cut it more than once with a horizontal line, which means its inverse is going to be cut more than once by a vertical line, which is the test for functions. So we've got to try and show that this function looks like the top picture and not like the bottom one. So you could sketch them if you want. You could sketch 2x and sketch log x and get a rough diagram and show that it looks more like picture 1 rather than picture 2. I don't really like sketching if I can avoid it, so I'm going to use the magic of calculus to answer this question. I'm going to analyze the derivative of f of x and see what's happening. So if I differentiate f of x, 2x is going to turn into 2, and log x differentiates to 1 over x. So there's my derivative. And now, because x is greater than 0, as the question mentioned, that means that 1 over x is also going to be greater than 0, and of course 2 is greater than 0. So because x is positive, my derivative is always going to be positive, which means if your derivative is always positive, it means your function is always increasing. So if a function is always increasing, it's going to look more like picture 1 rather than picture 2. So this is enough of an argument to say, all right, always increasing, it's never going to loop back on itself, therefore the inverse will be a function. That's plenty of an argument enough to get 1 mark. You don't need to go into huge detail here for 1 mark. Okay, that's the easier part. Part 2 is a bit more spicy. We've got let g be the inverse function of x. By considering the value of f of 1 or otherwise, evaluate g dash 2. Okay, so the tricky part here is that you're trying to find the value of the derivative of the inverse at 2, but obtaining the inverse function from the original using algebra is going to be really freaking challenging. So we've got to try and look for a shortcut here. All right, we'll take the hint of the question, which says to consider f of 1. All right, let's consider it. So f of 1 is 2 times 1 plus log 1. Log of 1 is equal to 0, and 2 times 1 is 2. So we get f of 1 is equal to 2. That tells me that the function, the original function, passes through the point 1, 2. So what information does this give you about the inverse? Well, the inverse is going to be the reverse of that. So g of x is going to pass through 2 of 1. Okay? Now, a cool little factoid that is definitely worth knowing for the HSC that makes a question like this, which is meant to be pretty scary, it makes it very straightforward, is the knowledge of the relationship between gradients of functions and inverse functions. By that I mean, the gradient, or the derivative, of the original function at 1, 2 is going to be the reciprocal of the gradient of the inverse at the inverse point 2, 1. Okay, this is because when you go from a function to an inverse, the gradient, which is rise over run, changes to be run over rise. Okay, so this is the reciprocal relationship between gradients of functions and inverse functions, which is a really fun sentence to say. What that tells me is that the value of the derivative of the inverse at 2 is the reciprocal of the value of the derivative of the original function at the original point. Okay, so f dash at 1 is the reciprocal of g dash at 2. And if you know that, now this question is just super easy because we have the derivative. So we have the original derivative. We're just gonna sub in 1 and then just take the reciprocal. Okay, so the reciprocal of the reciprocal of 2 plus 1 over 1 is 3. Reciprocal of that is 1/3, and that right there is your answer. How easy is that? So this wall text here. Really important to know. I would suggest writing it down if you haven't already covered it in class to prepare for your HSC. Okay, that was a lot of fun. Hopefully those questions gave you a bit of an insight to help you with your study. Of course, finishing off with a millennial gift to remind you that I am very, very old. In fact, I'll be even slightly older next week. Oh my God. Okay, hopefully, yeah, this helps you with your study. If there are any Extension 2 students watching and would like one of these for Extension 2, you just got to get this video to more than pi to the power of 5 views, and then I will find time to make one for the Extension 2 exam from last year before the HSC, which is in a couple weeks at time of recording. Anyway, good luck with your study. If you're stuck on any questions, you can hit up the McGrathematics Instagram and send me questions, and I'll get back to you whenever I'm available. Other than that, thanks for watching, and I hope you're learning, and I'll see you in the next video. Bye for now. Not forever.